Welcome to my talk on GPU computing using Vulkan and Kompute for cross-vendor graphics cards. My name is Alejandro Saucedo. I am Engineering Director at Seldon Technologies, Chief Scientist at the Institute for Ethical AI, and Member at Large at the ACM. So today we're going to be delving into a very interesting topic. We're going to be covering some of the key concepts of parallel processing GPU computing. We're going to be talking about the Vulkan SDK and its core components, how it works. We're going to be introducing the compute framework and how it simplifies the Vulkan SDK for computing purposes. And we're going to be covering a set of hands-on examples. There's going to be a lot on this talk, so let's dive straight into it. So first, the motivations of parallel processing. So we're going to be referencing this research survey that collected insights from 227 papers around parallel processing in AI. And it provides some really interesting insights of something that we may already be fully aware, which is the trend of adoption of GPUs and general processing in the scientific computing space. And the key things in here that have been really interesting, I do recommend you to check the full survey, is that a lot of the functions and a lot of the paradigms that are seen in this area of scientific computing and general processing tend to be highly parallelizable, or at least there has been abilities to reduce these functions into highly parallelizable components. There's also been a lot of different approaches to leverage concepts like micro-batching or processing multiple data points at the same time to leverage the hardware parallel capabilities and architecture of these graphics cards or specialized TPUs. And there's been other areas of research that have been also exploring and how to leverage these parallel processing components by breaking down these functions themselves, the processing, into fractions that then can be grouped in. And it's interesting that in the survey, not only they cover the concept of parallel processing, but also the trend towards distributed processing and the concepts and research that has come out of this, which is why I highly recommend you to check out the paper itself if you have time. Let's delve one level deeper into the actual hardware itself. And this is going to be important as it will provide you an intuition of why things may actually be designed as they are, as you delve into the code. And basically, the key concepts that we need to grasp, just build an intuition, is that graphics cards and GPUs themselves break down into the concept of computational grids, blocks, and threads. And each of these components will have different properties, but ultimately they are built in this way from a hardware perspective towards ensuring optimal access to memory, optimal processing. What is really interesting is that, as it may already be intuitive, there are distinct host and GPU device address spaces, which means that, for example, RAM is not going to be accessible to the graphics card for the processing, but similarly, or well, to a certain most extent, but similarly, there will be things like shared GPU memory access that the CPU will have access to, sacrificing some speed of processing. But then there's also going to be device only or graphics card only address spaces, which then the CPU won't have access to. And this is something really interesting, which we'll be coming back to, as we will see that the way that the Vulkan SDK is built is abstracting some of this to allow you to interact with it in a much more intuitive way. Similarly, the different address spaces within the graphics card themselves reflect different regions of locality of your program, and this will be important as you perform optimizations in different areas of the code, making sure that you're leveraging the right language and instruction components to ensure that you're not adding bottlenecks or adding long memory sort of like read wait times. So this is something that we will see also is important. And just to provide a little bit of an example that would allow you to see this as an intuitive perspective is that the GPU in itself is going to be a potentially separate component to your CPU code. So if you're writing your specific program, you're going to be interacting with the GPU as if you were interacting with, let's say, a remote server. Of course, this is not completely correct, but you will see that the way that the Vulkan SDK is built allows us to interact with the GPU as if it was a separate, different component. And this will become a little bit more intuitive. In terms of the ecosystem, of course, we delve into a lot of challenges because of the heterogeneity of the hardware that is involved in here. Multiple different graphics cards, multiple drivers, multiple players, and then, mobile phones as well. You have also different frameworks that allow you to leverage this or not. But from that perspective, we will see some of the motivations of why Vulkan has simplified a lot of this field. So Vulkan itself, what is it? It is a framework that aims to provide interoperability and to provide access into GPUs in a way that is performant and in a way that provides access on the specs, given that it is open source, right? And this is something that definitely brings a lot of benefit because it has the openness features that allow it to bring in different players to contribute and different stakeholders to make it better. Similarly, the organization that oversees the governance of this project is called the Kronos Group. This is basically a cross-industry member-based organization that has basically contribution and access from a broad range of different players. So you can see here, we can play Where's Waldo on the Kronos membership, given that there are so many different players. There is a lot of advantages and disadvantages within the Vulkan SDK. The main advantages is that it's low level with rich access to the underlying hardware. You get full access to the GPU and it's full powered from a hardware level. There is a C-style API as its core interface for developing your GPU applications. So, as what you see is what you get. You don't lose in regards to abstraction of the programming language when you're interacting with it. It's very close to the hardware. It provides the platform that actually provides that governance, consists of a broad range of top industry leading players to continue the development of the framework. And it is highly compatible across multiple platforms, multiple GPU providers, NVIDIA, Qualcomm, AMD, you name it. Some disadvantages is that this low level and rich access to components leads into very verbose code. And then similar with the C-Star API, it results in not only very verbose code, but a very sort of specialized requirement on the individuals building the initial layers to ensure that everything is done as it's intended to, which means that there's a lot of richness as opposed to complexity, richness in the interface that needs to be dealt with. This broad range of top players, of course, you can't have many players sitting on a table without having many voices and many opinions. And even though they're all pushing towards the best of the project, that will have some, offsets. And then similarly, the high compatibility across different platforms and hardware means that it has to service all of these different components, resulting in a very rich interface, which ultimately is good, given that it provides that low-level access, but then results in a lot of complexity. And when building Vulkan applications, it tends to have this very simple architecture. You have your Vulkan application at the very top, which it owns all of the subcomponents. You can create an instance, which ultimately is able to interact with multiple physical GPU devices. The physical device is the component, the Vulkan SDK C++ component that references your actual hardware, your physical graphics card. And then you can create views or windows to those hardware graphics cards. So this is basically your logical device, or often referenced as just device. Each device can have multiple queues. So these are actually your physical queues, and we're going to be actually talking about the queues in a little bit more detail in a practical use case. And this is to what I was talking about, the intuition, the way that Vulkan allows you to interact with your GPU is by submitting commands. And these commands are instructions to carry out code executions within the GPU. And this is carried out in a way asynchronously from the perspective of the CPU, ultimately you providing the commands for the graphics card to execute, and then just, perhaps listening to the completion of those themselves, right? And that is done through the concept of command buffers. And each command buffer can have specific memory addresses allocated to it, like what is Vulkan buffers, right? So this is basically the data that is used in those instructions. Now, here's where the richness comes with the Vulkan SDK. You can have multiple instances within a single application. You can have multiple physical devices, and each physical device can also have multiple logical devices, each with a separate queue that is being submitted to, right? So with this, you can already see that there is a lot of flexibility within the SDK. Now, when it comes to those commands that are submitted, you can actually submit quite rich instructions with it. And the way that you're able to submit actual, instructions that would be akin to code that would be run in the GPU is through the concept of pipelines, right? These pipelines are basically the core processing component that binds the specific code or algorithm to run with the data that is required, right? And from that perspective, that code is referred as the shader, right? So this is your shader code, your GLSL, which is like a language that you can use to write GPU code, et cetera, et cetera. And then descriptor sets are basically containers that reference the different buffers or addresses in the GPU space, right? So this is basically components that say, well, I want to run this specific program with these specific buffers, right? So that's basically it. In terms of pipelines, there's different type of pipelines, mainly the graphics pipeline and the compute pipeline are the one that we're going to cover here. The graphics pipeline, as you can see, there's much broader set of options. We're not going to be delving into that. We're going to be just talking about the compute pipelines, which consist of that algorithm or shader and the specific buffers to use for that processing, right? So what is the life in a Vulkan program? So let's see what actually happens normally when we interact with a Vulkan program. We would initially set up the physical device, so the graphics card and the logical device. We would actually specify the shader code that we would want to run on that physical device. We would create our compute pipeline to be able to run that. We would first take the memory from either the actual CPU visible memory into a GPU visible memory area. And then we will start recording the commands, right? We want to say, I want to basically run these specific things. And then before I send it into the instruction, I have to define a couple of things, such as maybe copy that piece of data into a GPU-only visible memory that the CPU doesn't have access to for potentially faster processing. We would then bind the pipeline to the shader. We would then specify what data should be used. And then we would dispatch that command right into the GPU so that then we would, once it's finished, copy the data back into the GPU visible memory, and then see it and print it on your CPU, right? So very simple. It only takes 500 to 2,000 lines of code just for the boilerplate. And this is where Vulkan Compute comes in, right? So basically enabling you to get started with compute in the GPU with dozens of lines of code instead of thousands, but as a core principle of compute, augmenting the Vulkan interface, given that it's so rich and so powerful, as opposed to abstracting it or hiding it. We've adopted a bring your own Vulkan design, which allows you to play nicely with existing Vulkan applications. So if you have some graphics application that uses Vulkan to render things, you would be able to actually use the same Vulkan instance and Vulkan application to leverage the Vulkan compute capabilities. And it uses non-Vulkan naming convention to avoid ambiguities of like, is this buffer from Vulkan or from this other library? Just as, this is something that we thought is very important. Other high-level features is that, of course, we have the C++ interface that is the core first-class citizen, but also we have Python bindings and a Python interface. We have explicit GPU, CPU memory ownership, which is basically ensuring and minimizing memory leaks, but also providing an ability to say explicitly when something is managed by compute versus something that you've provided yourself from an existing Vulkan application. There's granular access to the GPU queues. We're going to talk a little bit more about that. There is actually, a single header file to get started easily, but you can also use the usual structure of the C++ files. And there's integration with mobile, so through the Android NDK, and there's examples for that, as well as integration with game engines, particularly with Godot, which is also part of the FOSDEM conference. So what does compute look like, and how does it reference back to the Vulkan things that we've covered? So compute all consists of the top level of a manager, right? And the manager is the one that actually is able to have ownership of the relevant resources that are not already managed by external Vulkan applications. This is basically your device and your Vulkan queue, right? Each manager can have multiple sequences, right? So the sequences are basically aggregate or bulk set of things that can be executed in the GPU, right? So it manages the operations to run in the GPU itself. And the sequence can have one or many operations. These operations are actually individual commands that would be executed in the GPU itself. And each operation can have a set of tensors, right? A single tensor, which a tensor is basically just akin to a Vulkan buffer and a Vulkan memory address. And optionally, it can have what we refer to as algorithm, a compute algorithm. And the compute algorithm abstracts the pipeline, the compute pipeline itself, as well as the relevant shader modules, the descriptor sets, if you remember the containers that reference the specific, in this case, tensors or buffers. So this is basically how it simplifies it, right? So you have a orthogonal naming convention that is still one-to-one with your Vulkan components, which means that you still have full power and full access to all of the Vulkan goodies, whilst providing you with a augmented interface towards it. So now let's see what this looks like in C++. We would first create a manager, right? So this is basically what we were referring to. This is the overarching component that allows us to manage all of our underlying components. This manager then allows us to create tensors, right? So this tensors and this function is a helper function. You would actually normally, do this as a separate, operation, but it has some helper functions if you want to just interact with it easily. Here we're initializing tensors, which actually created in the GPU space and copy it into device-only memory, and you can actually specify that explicitly. We then define our shader codes, which in this case, what we're doing is just performing a multiplication. So 3 tensors, 2 input ones, A and B, and then the output one, which basically stores the output of that computation. So we're going to be just multiplying each of these sort of components and then providing the output in the third one. And the way that you're able to run it is by actually executing it through the manager. So you can actually evaluate an operation. Right. So in this case, we're evaluating an operation directly. We can actually, record a set of them, which we're going to see in a bit. So we're saying run this operation with a raw string algorithm, which in this case is this one, using these 3 tensors. Right. So it's going to actually run this. It's going to run this in the GPU, which is basically the simple multiplication. And then once it's done, we can actually map the results back from the GPU only memory to our CPU visible memory. And that then allows us to print the data that is held on the tensor output, which it would be basically 2, 4, and 6. We also have the Python bindings, which would look very, very similar. What that would look like is we create our manager, we then build the tensors, very similar. We then define the shader, which in this case, as you can see, we're using this library called PyShader, which allows us to define that as Python. And here it's much more intuitive. We can see that the multiplication is happening, in here, and this actually converts into the underlying components. Then we actually run that shader, right, with the specific tensors, and we can then copy back the data from the GPU to then print it, right? Very simple. That's basically all we need to do to run our first compute, right? So now what we're going to be doing is delving into a few more sort of advanced components of compute. And let's cover them from a theoretical perspective first. So some deeper optimizations is that we can actually do what we just did, right? So run a single command or operation through the manager, right? So this basically records the command, runs it, and then waits until it's finished, right? But what we can do as well is we can actually record multiple operations and run them in batch, right? So we can actually record multiple operations in a sequence and then execute them in batch. And that means that there's less time that is spent actually recording those, right? So this is actually a benefit of doing this stuff. But also with compute, we can run asynchronous, we can run and evaluate operations and sequences asynchronously, which means that we would basically, run in the CPU. So this is basically CPU time and GPU time. We would be able to execute it, and then this would basically run, and it may finish at some point. We can actually use a fence or a lock to be able to know when it's finished, or we can use the await command, which we're going to show in a bit. And then you can actually run another one, right? So this basically allows you to not get interrupted in the CPU time. And the last one is basically running concurrent operations. And this may be a little bit confusing, but will make a bit more sense. But basically what this means is that you're running concurrently multiple batch operations at the same time. So you're submitting two, both of them are running in parallel concurrently in two GPU queues, right? And to make a bit more sense of that is that at the hardware level, the GPUs themselves come with the concept of different GPU queue families, family types and queues, right? So in the case of my GPU, a 1650 NVIDIA card, it actually has three different type of families, queue families. It has a graphics family, a transfer family, and a compute family. In the graphics family, it has 16 physical queues. In the transfer family, 2 physical queues, and the compute family, 8 physical queues, right? And what it basically says is that from a hardware perspective, my graphics card is able to run in parallel one graphics card and one compute card. One graphics family queue and one compute family queue. And what that means is that if I was to submit one command into a graphics and one command into a compute queue, they would both be able to run concurrently, right? Physically concurrently. But conversely, if I was to submit 2 operations into multiple queues within, let's say, the graphics family, they would not run concurrently, right? It would run sequentially. So first, it would run the one in the graphics queue index 0, and then the one in graphics queue index 1, right? So this is the key thing. We can actually leverage hardware concurrent in single graphics card using multiple family queues. And what we're going to be doing is we're going to be leveraging Vulkan Compute to be able to run each sequence in a different hardware queue, right? And what this really looks like, and it will become a little bit more intuitive, is that instead of just initializing our manager with the defaults, we can initialize it with a specific device ID, which in this case, it would be the actual graphics card that I want to use. And then I can specify, well, I want 2 queues to be explicitly allocated. I want to use a graphics queue, which is index 0, or family index 0, and a compute queue, which is graphics index 2, right? So now I have those 2 available. I will then be able to just create all of the tensors as I was doing it, and then I can create my sequences explicitly. So I want to create a named sequence called graphics queue sequence using the first one that I selected, and then the second one, compute queue sequence, using the second one, which is actually the compute family. What that means is that I can actually run those asynchronously. So manager dot not just eval up, but eval up async, right? So this one actually allows me to submit it asynchronously. So I would submit this first one asynchronously to the graphics queue, and the second one asynchronously to the compute queue. And then I would be able to await for them at the same time. They would then run concurrently, right? And this is the emphasis, that it's actually running concurrently. And this may be a little bit sort of like counterintuitive, given that you may already think to yourself, well, it's a GPU, so doesn't everything get just run concurrently in parallel? Well, so ultimately, this is actually concurrency within the already parallel architecture, but it's ultimately concurrency in the sort of like hardware queues that allow you to submit batches of commands that would then run actually hardware concurrently. So this is the key sort of nuance difference to bear in mind. Unfortunately, we actually have reference documentation that covers this in much more detail, much more intuitive perspective. And this is something that I would actually recommend. We have a set of other tutorials, GPU accelerated machine learning, Android app integration, Go.game engine, where you can actually delve into the C++ code and try it yourself. Of course, we have some key priorities within the high-level roadmap. Things like integrating as backend of existing scientific computing framework. This is something that initially motivated the creation of Kompute. We wanted to actually create a broader set of default operations available. We were using the algo up, which is the one that allows you to run the shader, but we'd love to have, things like, I don't know, parallel sum operator or things like that, that we would be open to exploring. And then examples or Fourier transform operation or something like that. And then we also want to add more examples. So if you're keen to test it or try it with another different application and you come up with something, we'd love to actually add more examples, more tutorials in Kompute. And get involved, right? So if you're keen to explore what's available, in our repo, you can actually go into the good first issues, right? So all of the issues labeled good first issues. So please do give it a try on those ones, and we're more than happy to provide guidance and also sharing thoughts or suggestions, via our current open issue number 52, which is basically just open for people to ask for suggestions. So if you want, access it on github.com/ethicalml/VulkanCompute, and you'll be able to find, everything you need together with the documentation. If you have questions, feel free to open an issue, and we're going to be more than keen to welcome you and get you up and running to get using it or contributing it. And with that said, I have been able to go through all of the key concepts on this talk around GPU computing using Vulkan and Kompute for cross-vendor graphics card. Thank you very much for joining, and looking forward to explore different ideas around the parallel processing realm and the Vulkan ecosystem. Thank you very much.